Assalamualaikum warahmatullahi wabarakatuh. My name is Nurul Aina Affiqah binti Muhamad. Today, my friend and I are going to present Chapter 6 of Organometallic Chemistry, which is some uses of organometallic compound. Organometallic compound has the properties of catalyst. It able to undergo the reaction of oxidation and reduction process. In the industry, there are a lot of organometallic compounds that are used as catalysts. Moreover, most of them are employed for reduction and oxidation process. In this chapter, my friend and I are going to explain only 4 of these catalysts with different process. I am going to explain on the first example, which is bicyclopentadienyl tantalum trihydride as the catalyst for deuteration reaction of benzene. So, what is deuteration reaction of benzene is deuteration reaction is the replacement of hydrogen atom in the benzene with deuterium atom. So, the first step of this mechanism is the bicyclopentadienyl tantalum trihydride will lose 2 hydrogen atoms to form 16 electrons of cyclopentadienyl tantalum hydride, which it will then react with benzene molecule to form back 18 electrons of Cp2TaH2PH, where the phenyl group is sigma bonded to the metal. Next, on the third step, the Cp2TaH2PH will lose another 2 hydrogen atoms to form 16 electrons of Cp2TaPH. It will then undergo oxidation addition, where 2 atoms of deuterium will be added to form Cp2Ta-D2PH. On the last step, Cp2Ta-D2PH will eliminate C6H5T and leaving behind C2Ta-D. However, this step is not finished yet. All the hydrogen atoms in the benzene should be replaced with deuterium atom. So, step 2 until step 5 will be repeated until all the hydrogen atoms are replaced. That is all from me. I'm going to pass to Nadhirah for her to explain on the second example.
Bismillahirrahmanirrahim. Assalamualaikum. My name is Nurul Nadhirah binti Ramli, and I'll be explaining about the example 2, which is the RHCO2I2 as a catalyst in the Monsanto acetic acid process. So this is the overall reactions, which is the CO and H2 syngas will react with copper and zinc and will obtain methanol. This methanol will proceed with reacting with the carbonyl, rhodium and iodide to obtain acetic acid as the final product. Okay, for the Monsanto acetic acid process, using the catalyst of RHCO2I2, there are 7 step process that involve. The first one is the iodide will convert the methanol into the methyl iodide, producing water as its byproduct. The step 2 is rhodium will react with CO and iodide to produce the catalyst that will be used in this process, which is the RHCO2I2. And next, the step 3 is the catalyst will undergo oxidative addition with the metal iodide, producing CH3RH2I3. Next is the step 4, which is the insertions of carbonyl into RHCH3 bond in the CH3 RHCO2I2 producing the CH3OH RHCO2I3. Step 5, if the CH3RHCO2I3 undergoes the reductive elimination, releasing the CH3COI and regenerating the catalyst from the previous, which is the RHCO2I2. Step 6 is the CH3COI reacts with the H2O that was produced in the step 1 from the converting of the iodide and the methanol into methyl iodide to form the CH3COOH and HI, which is the acetic acids. Okay, so the Monsanto acetic process is which is the step 3 and 5, which that I previously mentioned, that was repeatedly in the cyclic manner, while the step 1 is continued to supply the methyl iodide with a byproduct of the H2O. Lastly, the step 7 is to complete the productions of acetic acid by the reaction below, which is the CH3COI and the H2O producing the CH3COOH and HI. Okay, in this slide, you can see the overview of the Monsanto acetic acid process, which is a cyclic cycles of the step 3 and 5, like I mentioned before, which is a cyclic manner, and with the step 1 providing with the methyl iodide and the byproduct, which is the H2O. It started from the catalyst itself, which is the RHCO2I2, and ended with the catalyst again. So that's all for the Monsanto acetic acid process, which are with RHCO2I2 as a catalyst.
Okay, now we will be move on into the third example in this chapter, which is Wilkinson catalyst. Wilkinson catalyst is a very famous one in organometallic chemistry. Before we further our discussion, we must know what is Wilkinson catalyst. So, let me share with you guys what is Wilkinson catalyst. Wilkinson catalyst is a common name for chloro-3-triphenylphosphine rhodium 1. The chemical formula is stated as above. Everything in this world has its own purpose. Same goes to the Wilkinson catalyst. The main purpose of the Wilkinson catalyst is it catalyzes the reaction of hydrogenation of alkene. Wilkinson catalyst was found by a scientist named Geoffrey Wilkinson. Okay, as shown above, that is the structure for Wilkinson catalyst complex. As it for basic properties, Wilkinson catalyst complex is a square planar complex with 16 electrons. Okay, as for its physical appearance, Wilkinson catalyst is a red-brown solid that is soluble in hydrocarbon solvent. Lastly, Wilkinson catalyst can be formed by this reaction. Okay, next we will be move on into the hardest part for this chapter, which is mechanism. As shown there, that is the cycle for the mechanism of hydrogenation of alkene using Wilkinson catalyst. But don't worry, I'll guide you step by step, which include 5 steps in this mechanism. Okay, first step. Okay, here we have complex A, which is Wilkinson catalyst that contains 16 electrons, where it undergoes a dissociation of 1 ppH3 from it, which gives another complex with 14 electrons, or I name it as complex B. Okay, step 2. Here we have complex B with 14 electrons. Okay, complex B will undergo the oxidative addition of H2 into the complex, which give another complex, I name it as complex C, with 16 electrons. Step 3. The complex C will undergo another addition, which addition of propene, which give 18 electron complex, and we call it complex D. Okay, next for step 4. Step 4 is all about the intramolecular reaction within the complex. Here we have complex D with 2 hydrogen and 1 propene. So there will be an intramolecular transfer of hydride from a metal, which is radium, into the olefin C double bond C, which will produce another complex with 18 electron, or we call it as complex E. Okay, finally for step 5. In step 5, the reductive elimination of a propane from complex E will be occurred, and it will produce the complex B back, which is Wilkinson catalyst. Therefore, the hydrogenation of propene to propane has completed. With that, we have done the whole mechanism for the hydrogenation of alkene.
So, Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. My name is Hidayati Nabihah binti Muhamad Zamri, and now I will explain to you about fourth example, which is Waker oxidation. So, what is Waker oxidation? Waker oxidation is the process of oxidation of ethylene to acetaldehyde in the presence of palladium 2 chloride as catalyst. It is the first homogeneous catalysis using organopalladium. As you can see the equation below, this is the general equation of Waker oxidations. As you can see on the next slide, this is the overall mechanism of the Waker oxidation. As you can see, the ethylene was react with catalyzed PdCl2, catalyst CuCl2, oxygen H2O, and solvent DMF to get the acetaldehyde. So, now I will explain to you about the mechanism of Waker oxidation. So, Waker oxidation includes of 2 steps. So, for the first step is water nucleophile. The mechanism of Waker oxidation has been studied both experimentally and theoretically. The first step of the Waker oxidation involves of the coordinations of the alkene to the palladium center to form the pi complex. Evidence for this step is provided by the relative sluggishness of electron-poor alkene, which generally require higher catalyst loading than inactive alkenes. Hydroxyl palladiations then occur to yield either zwitterionic complex at the structure 3 or neutral complex at 4, depending on the mode of hydropalladiations. Study employing deuterated substrates suggests that beta hydride elimination then occur to afford enol complex, as you can see at the step 5, which reinsert into the PDH bond to afford the complex. Next, computational studies support the involvement of chloride-assisted reprotonization in the subsequent step, which afford the product of palladium 2. Oxidation of palladium by Cooper-2 then occur, regenerating palladium 2 species. The role of Cooper-2 in the mechanism is poorly understood at the present. So, I will continue. The mode of hydroxypalladation is an important issue for the Waker oxidations. Hydroxypalladation may occur either in a syn fashion through an ineosphere mechanism or in anti-fashion via nucleophile attacks on the coordinated alkene. Although the stereo center in 4 is ultimately destroyed upon elimination, the mode of hydroxypalladation can influence the site selectivity of the reaction. Markovnikov type addition of water to the more substituted carbon of the alkene form a methyl ketone, while attack of water at the less substituted position ultimately yield an aldehyde. The mode of hydroxypalladation has been shown to affect the distribution of ketone and aldehyde products. And it also important in stereoselective Becker cyclization reaction. Okay, for the second step is prevailing mechanism, which is alcohol nucleophiles. Alcohols may also be employed as nucleophile in the Becker process. The initial step of the mechanism are similar to those for the Becker oxidation for the water, but the mechanism diverge at alkoxy complex at the 11 step. Elimination of palladium occurs to generate an oxocarbonium ion, which may be captured by the solvent to generate an acetal. Small amounts of vinyl ether products support the intermediacy of complex. Okay, that's all from me and my friends on Chapter 6, the uses of some organometallic compounds. Thank you for listening, and I hope you guys get some information about this topic. Last but not least, stay at home and stay safe. Bye!